Hi dear students, welcome. Let us discuss about unit number 4, that is chemical kinetics of second PUC chemistry. For the main exam there will be total 8 marks from this chapter and there will be 3 types of questions from this chapter. In the question paper, question number 4 will be from this chapter which carries 1 mark and question number 13 from this chapter carries 2 marks and question number 30 from this chapter carries 5 marks. Let us know the definition of chemical kinetics. It is a branch of chemistry which deals with the study of reaction rates and their mechanisms. These kinetic studies help us to determine the rate or speed of a chemical reaction and also to describe the conditions by which the reaction rates can be altered. The factors affecting the rate of a reaction are concentration, temperature, pressure, and catalyst. The different types of chemical reactions are fast reactions, example is precipitation of silver chloride. Moderate speed reactions, examples are inversion of cane sugar and hydrolysis of starch. Very slow reactions, example is rusting of iron in the presence of air and moisture. A rate or velocity or speed of a chemical reaction can be defined as the change in the concentration of a reactant or product in unit time. Unit of rate of a reaction is concentration per time or mole per liter per second or atmosphere per second. A rate of a reaction can also be expressed in terms of the rate of decrease in the concentration of any one of the reactants or the rate of increase in the concentration of any one of the products. For example, consider a reaction, reactant gives product, that is capital R gives capital P. A rate of disappearance of R is equal to decrease in the concentration of R divided by time taken, which is equal to minus delta of R divided by delta T. A rate of appearance of product is equal to increase in the concentration of product divided by time taken, that is equal to plus delta P divided by delta T. Since delta R is a negative quantity, as the concentration of reactant is decreasing, it should be multiplied by minus 1 to make the rate of a reaction a positive quantity. The rate of a reaction measured over a long interval of time is called an average rate of a reaction. Average rate depends upon the change in the concentration of reactants or products and the time taken for that change to occur. The rate of a reaction measured at very small interval of time is called instantaneous rate. Instantaneous rate is the average rate at the smallest time interval, say dt, that is when delta t approaches 0. Instantaneous rate is given by R instant is equal to minus dr divided by dt is equal to dp divided by dt. For a reaction AA plus BB gives CC and DD, rate is equal to minus 1 by A delta A divided by delta T, which is equal to minus 1 by B into delta B divided by delta T, which is equal to plus 1 by C into delta C divided by delta T, which is equal to plus 1 by D into delta D divided by delta T. For a reaction, Hg liquid reacts with Cl2 gas to give HgCl2, which is solid. Rate for this reaction is equal to minus delta Hg divided by delta T is equal to minus delta Cl2 divided by delta T, which is equal to plus delta HgCl2 divided by delta T. For a reaction, 2Hi gas gives H2 gas plus I2 gas. The rate of this reaction is equal to minus 1 by 2 delta Hi divided by delta T is equal to delta H2 divided by delta T, which is equal to delta I2 divided by delta T. For the reaction 5Br minus plus BrO3 minus plus 6H plus gives 3Br2 plus 3H2O. Rate for this reaction can be written as rate is equal to minus 1 by 5 delta Br minus divided by delta T is equal to minus delta BrO3 minus divided by delta T, which is equal to minus 1 by 6 delta H plus divided by delta T, which is equal to 1 by 3 delta Br2 divided by delta T, which is equal to 1 by 3 delta H2O divided by delta T. For a gaseous reaction at constant temperature, concentration is directly proportional to the partial pressure of a species. Hence, rate can be expressed as the rate of change in partial pressure of the reactant or the product. For example, N2 gas reacts with 3H2 gas to give 2NH3 gas. Rate is equal to delta P of N2 divided by delta T, which is multiplied by minus 1, which is equal to minus 1 by 3 delta P of H2 divided by delta T, which is equal to plus 1 by 2 into delta P of NH3 divided by delta T. Let us know about factors influencing the rate of a reaction. Rate of a reaction depends upon the experimental conditions like concentration of reactants, pressure in case of gases, temperature, and catalyst. Dependence of rate on concentration. The rate of a chemical reaction at a given temperature depends on the concentration of one or more reactants and products. The representation of rate of a reaction in terms of concentration of the reactants is known as rate law or rate equation or rate expression. The rate of a reaction decreases with increase in time as the concentration of reactants decreases. But rates increase when reactant concentrations increase. So, the rate of a reaction depends upon the concentration of the reactants. Consider a reaction AA plus BB gives CC plus DD, where small a, b, c, d are the stoichiometric coefficients of the reactants and the products. The rate expression for this reaction is rate is directly proportional to concentration of A to the power x into concentration of B to the power y, or rate is equal to small k into concentration of A to the power x into concentration of B to the power y. Differential rate equation is dr by dt is equal to k into A to the power x into B to the power y, where k is called proportionality constant, that is rate constant. The equation which relates the rate of a reaction to the concentration of reactants is called rate law or rate expression. Thus, rate law is the rate expression in which reaction rate is given in terms of molar concentration of the reactants, with each term raised to some power. For example, 2NO gas reacts with O2 gas to give 2NO2 gas. Rate is equal to small k into concentration of NO to the power 2 into concentration of O2. The differential form of this rate expression is dr by dt is equal to k into concentration of NO to the power 2 into concentration of O2. Let us know about reactions and their experimental rate expressions. For reaction, chloroform reacts with chlorine to form carbon tetrachloride and HCl. Rate for this reaction is rate is equal to k into concentration of chloroform into concentration of chlorine to the power 1 by 2. Similarly, ethyl acetate reacts with water to form acetic acid and ethanol. Rate for this reaction is equal to K into concentration of ethyl acetate to the power 1 into concentration of H2O to the power 0. In the above reactions, the exponents of the concentration terms are not the same as their stoichiometric coefficients. Thus, we can say that rate law for any reaction cannot be predicted by merely looking at the balanced chemical equation, that is theoretically, but must be determined experimentally. Order of a reaction is the sum of the powers of the concentration of the reactants in the rate law expression. Order of a reaction can be 0, 1, 2, 3, and even a fraction. A zero order reaction means that the rate of a reaction is independent of concentration of the reactants. A rate is equal to K into concentration of A to the power 1 by 2 into concentration of B to the power 3 by 2. Order for this rate is the power should be added. 1 by 2 plus 3 by 2 gives 2, that is order is 2. Rate is equal to K into concentration of A to the power 3 by 2 into concentration of B to the power minus 1. Order for this rate is the power should be added 3 by 2 plus of minus 1, which gives half. Let us know about different types of chemical reactions: elementary reactions, complex reactions, conjugative reactions, reverse reactions, and side reactions. The reactions taking place in one step are called elementary reactions. The reactions in which a sequence of elementary reactions gives us the products are called complex reactions. The reactions which involve a series of intermediate steps are called conjugative reactions. Example: oxidation of ethane to carbon dioxide and H2O passes through, in which alcohol, aldehyde, and acid are formed as intermediates. The reactions which involve interconversion of reactants and products is called reverse reactions. The reactions which involve the formation of more than one product are called side reactions. Nitration of phenol gives orthonitrophenol and paranitrophenol. For zero order reaction, order is 0, but unit of rate constant is mole per liter per second. For zero order reaction, first order reaction order is 1, unit of rate constant is per second. For second order reaction, order is 2, and unit of rate constant is liter per mole per second. The molecularity of a reaction helps in understanding its mechanism. The number of reacting species, which may be atoms, ions, or molecules, taking part in an elementary reaction, which must collide simultaneously in order to bring about a chemical reaction, is called molecularity of a reaction. The reaction which involves one reacting species is called unimolecular reaction. For example, decomposition of ammonium nitrate. Here, one molecule of ammonium nitrate gives one molecule of nitrogen and two molecules of water. Since reacting species is one, it is an example of unimolecular reaction. Bimolecular reactions involve simultaneous collision between two species. For example, dissociation of hydrogen iodide, where two molecules of hydrogen iodide collide with each other to form one molecule of hydrogen and one molecule of iodine. Tri or termolecular reactions involve simultaneous collision between three reacting species. For example, two molecules of NO react with one molecule of oxygen, that is, totally three reactant molecules collide with each other to form two molecules of NO2. Polymolecular reactions are very rare and slow to proceed, justify, because the probability of collision and reaction between more than three molecules is very small. Hence, polymolecular reactions are very rare and slow to proceed. The complex reactions involving more than three molecules must take place in more than one step. In such cases, the overall rate of the reaction is controlled by the slowest step in a reaction, which is called rate determining step, that is RDS. For example, the decomposition of hydrogen peroxide, which is catalyzed by iodide ion in the presence of alkaline medium, it gives two molecules of H2O and one molecule of oxygen. A rate equation for this reaction is rate is equal to minus d of concentration of H2O2 divided by dt is equal to small k into concentration of H2O2 into concentration of I minus. This reaction is first order with respect to both H2O2 and I minus. Actually, this reaction takes place in two steps. In the first step, H2O2 reacts with I minus to form H2O and IO minus. In the second step, H2O2 reacts with IO minus to give H2O, I minus and O2. Both the steps are bimolecular elementary reactions. The species IO minus is called intermediate because it does not appear in the overall balanced equation. The first step is the slow, which determines the rate of a chemical reaction. Hence, first step is called rate determining step. Let us know the differences between order and molecularity. Order of a reaction is an experimental quantity. Order can be 0 and even a fraction, but molecularity cannot be 0 or non-integer. Order is applicable to elementary as well as complex reactions, whereas molecularity is applicable only for the elementary reactions. For a complex reaction, molecularity has no meaning. For a complex reaction, order is given by the slowest step, and molecularity of the slowest step is same as the order of the overall reaction. Let us know the differences between order and molecularity. Order is the sum of the powers of the concentration of the reactants in the rate law expression, but molecularity is the number of reacting species taking part in an elementary reaction which must collide simultaneously in order to bring about a chemical reaction. Order can be 0 and even a fraction, but molecularity cannot be 0 or a non integer. Order is applicable to elementary and complex reactions, but molecularity is applicable only for elementary reactions. Let us know how to derive an expression for rate constant of zero order reaction. Zero order reaction is the one in which rate of a reaction is proportional to 0 power of the concentration of the reactants. Consider reactant R gives the product P, for which rate is equal to minus d of the concentration of R divided by dt is equal to K into concentration of R to the power 0, which is equal to K into 1. Hence, dr is equal to minus K dt. On integration gives concentration of R is equal to minus Kt plus I, where I is integration constant. Initial concentration of reactant is equal to minus K into 0 plus I, because at time t is equal to 0, concentration of reactant becomes equal to initial concentration of the reactant. Hence, R naught is equal to capital I. From equation 1, concentration of R gives minus Kt plus R naught, because I is equal to R naught. Therefore, rate constant for zero order reaction, that is K, is equal to R naught minus R divided by T. Examples of zero order reactions are: first one is the decomposition of gaseous ammonia on a hard platinum surface at high pressure. Second one is the thermal decomposition of hydrogen iodide on gold surface. This is a graph where we plot concentration of reactant versus time, which gives a straight line with intercept r naught and slope is equal to k. Let us know how to derive rate constant expression for first order reactions. First, we need to know what we mean by first order reaction. The rate of the reaction is proportional to first power of the concentration of the reactant, is called first order reaction. For example, reactant R gives product P. Rate for this reaction is rate is equal to minus d of concentration of R divided by dt is equal to K into concentration of R to the power 1, which is equal to K into concentration of R. On rearranging, d of R divided by R is equal to minus K dt. On integration, we get ln of R is equal to minus Kt plus I. I is integration constant. Ln of R naught is equal to minus K into 0 plus I, because at time t is equal to 0, R becomes equal to R naught. Hence, ln of R naught is equal to I. From equation 1, ln of R is equal to minus Kt plus ln of R naught. Kt is equal to ln of R naught divided by R. Hence, rate constant K is equal to 1 by T ln of R naught divided by R, or K is equal to 2.303 divided by T into log of R naught divided by R. Examples of first order reactions are hydrogenation of ethene, and second examples are all natural and artificial radioactive decay of unstable nuclei. Third example is decomposition of N2O5 and N2O. These are the graphs for first order reactions. In the first case, we plot ln of R versus time, which gives straight line with intercept ln of R naught and minus slope is equal to rate constant, that is K. In the second case, we plot log of R naught divided by R gives straight line with slope is equal to K divided by 2.303. This gives a straight line passing through an origin. Let us know what do you mean by half-life of a reaction, that is T off. The half-life of a reaction is this time in which the concentration of a reactant is reduced to one half of its initial concentration. Hence, for a zero order reaction, rate constant K is equal to R naught minus R divided by T. At T is equal to T off, R naught becomes equal to 1 by 2 R naught. The rate constant at T off becomes K is equal to R naught minus 1 by 2 R naught divided by T off, or T off is equal to R naught divided by 2K. That is, the T off for a zero order reaction is directly proportional to the initial concentration of the reactants, that is R naught, and inversely proportional to the rate constant, that is small k. But for first order reaction, we already know rate constant, that is k is equal to 2.303 divided by t into log of R naught divided by R. At t is equal to t of R becomes equal to R naught divided by 2, and hence equation 1 becomes k is equal to 2.303 divided by t of into log of R naught divided by R divided by 2. T of is equal to 2.303 divided by k into log of 2, which is equal to 2.303 divided by k into 0.301, which is equal to 0.693 divided by k. Hence, for first order reaction, half-life period, that is T of, is constant, that is it is independent of the initial concentration of the reactant. But for zero order reaction, T of is equal to is directly proportional to initial concentration of the reactant. Let us know what is the meaning of pseudo first order reaction. It is a reaction which is not actually a first order reaction naturally, but made first order by increasing or decreasing the concentration of one or the other reactant. Examples are hydrolysis of ethyl acetate and inversion of cane sugar. Let us know about temperature dependence of the rate of a reaction. Most of the chemical reactions are accelerated by increase in the temperature due to increase in the number of activated molecules. For a chemical reaction with rise in temperature by 10 degree, the rate constant becomes double. For example, in the decomposition of N2O5, the time taken for half of the original amount of material to decompose is 12 minutes at 50 degree Celsius, 5 hours at 25 degrees Celsius, and 10 days at 0 degree Celsius. That means as the temperature decreases, the time taken for half of the to reduce half of the original amount of the material also decreases. The temperature dependence of the rate of a chemical reaction can be accurately explained by Arrhenius equation, that is small k is equal to capital A into e to the power minus Ea divided by RT, where capital A is the Arrhenius or frequency or pre-exponential factor, which is a constant and specific to a particular reaction. And here capital R is a gas constant and Ea is the activation energy measured in joules per mole. This is a picture where you can see the formation of HI through the formation of intermediate, where H2 reacts with I2 to form an intermediate which on decomposition gives two molecules of hydrogen iodide. In the graph you can see potential energy versus reaction intermediate, where H2 and I2 react together to form an activated complex, that is C, which on decomposition gives B, that is product, that is two molecules of hydrogen iodide. According to Arrhenius, this reaction occurs only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate. This intermediate exists for very short time, which undergoes decomposition to give two molecules of hydrogen iodide. Hence, the energy required to form this intermediate or a activated complex is known as activation energy or energy of activation, denoted by EA. This is a graph where we plot ln of k versus 1 divided by t, which gives a straight line with intercept ln of a and slope minus a divided by r, and the equation is ln of k is equal to minus ea divided by rt plus ln of a. If you consider two rate constants at different temperatures, we get an equation log of k2 divided by k1 is equal to ea into t2 minus t1 divided by 2.303 r into t1 into t2. Let us know about catalyst and its effect. A catalyst is a substance which increases the rate of a reaction without itself undergoing any permanent chemical change. An example is the decomposition of potassium chloride, that is KClO3, gives 2 molecules of KCl and 3 molecules of oxygen in the presence of catalyst MnO2, which increases the rate of a reaction. Okay, let us know about intermediate complex formation theory, which explains the action of a catalyst in a chemical reaction. According to this theory, formation of an intermediate complex takes place due to the chemical reaction between catalyst and reactants. In the second step, the decomposition of intermediate complex, which is very short living, to yield products and the catalyst. This is a graph of energy level diagram where we plot potential energy versus reaction coordinate. Here, in the absence of catalyst, reactants react together to form product which takes more time. But in the presence of a catalyst, reactants give products in a very short time. Hence, catalyst provides an alternate path by reducing the activation energy between reactants and products, and hence lowering the potential energy barrier between reactants and products. As per Arrhenius equation, lower the value of activation energy, faster will be the rate of a reaction. A small amount of the catalyst can catalyze a large amount of reactants. A catalyst does not alter Gibbs energy of a reaction. A catalyst catalyzes the spontaneous reactions but not the non spontaneous reactions. The catalyst does not change the equilibrium constant of a reaction, but it helps in attaining the equilibrium faster. That is, catalyst catalyzes the forward as well as backward reactions to the same extent so that the equilibrium state remains the same but is reached earlier. Let us know about collision theory of chemical reactions. Collision theory was developed by Max Strauss and William Lewis. Collision theory deals with the energetic and mechanistic aspects of chemical reactions. This theory is based on the kinetic theory of gases. According to this theory, the reactant molecules are assumed to be hard spheres, and the reaction occurs when the molecules collide with each other. The number of collisions per second per unit volume of the reaction mixture is known as collision frequency, denoted by capital Z. The factor which affects the rate of a chemical reaction is an activation energy. For a bimolecular elementary reaction, that is A reacts with B to give products, the rate of a chemical reaction can be expressed as rate is equal to capital Z of AB into e to the power minus Ea divided by RT, where ZAB is the collision frequency of the reactants A and B, and e to the power minus Ea divided by RT is the fraction of the molecules with energies equal to or greater than Ea. All the collisions do not lead to the formation of the products, but the molecules with sufficient kinetic energy, which is called threshold energy, and proper orientation undergo collisions which facilitate the breaking of old bonds between reacting species and the formation of new bonds to form the products. These collisions are called effective collisions. To account for an effective collisions, another factor, that is capital P, which is called probability or steric factor, is introduced. For a collision to occur, molecules must be properly oriented. Hence, rate becomes equal to P into Z of AB into e to the power minus Ea divided by RT. Thus, in collision theory, activation energy and proper orientation of the molecules together determine the effective collision and hence the rate of a chemical reaction. For example, formation of methanol from bromomethane depends upon the orientation of the reactant molecules. The proper orientation of reactant molecules lead to the bond formation of the products, whereas improper orientation does not give the products. You can see in the following reaction. In case of improper orientation, there will be no formation of products. But in case of proper orientation of the reacting species, there will be formation of intermediate which undergoes decomposition to form the products. Drawback, drawback of collision theory. This theory assumes atoms or molecules to be hard spheres, and also this theory ignores the structural aspect of atoms and molecules. Thank you.